Okay, good afternoon, everybody. It is really a pleasure to have with us Andrea Bianco this afternoon from the INAF-Osservatorio of Brera. And let me introduce briefly our guest. Andrea got his PhD in 2004 in materials engineering at Politecnico di Milano in collaboration with the INAF Brera on a thesis with title New Organic Materials for Optical Elements in Astronomy and supervised by Filippo Zerbi. Then he has been a postdoc first at Politecnico and then at ESF in Milan. And then since 2010, Andrea is full-time researcher at INAF Brera, based in Merate, I know. And his research activity focuses on the development of reliable devices with the required target performance. What this means will be very clear after this talk this afternoon. And the talk of Andrea has a title, Innovative Optical Elements for Astronomy, from the molecule to the on-sky device. So, Andrea, I'll give you the microphone. And you have 45 minutes, as you know, and please.
Okay, thank you, Michele, for the introduction and for the invitation. I'm just sharing the presentation. Okay, so this afternoon I hope to show you an approach we followed in the last years to develop optical elements in astronomy, starting from basic research on molecules. And I will show some examples yes, hope it will be interesting and not boring. There will be a little bit of chemistry and spectroscopy, molecular spectroscopy, for if something is not clear, or just stop me and ask me to explain. And yeah, I'll start from very basic things. We deal with optical devices, and we have to go back more than 4 centuries, and Galileo Galilei exploited the telescope to look at the sky, and it was very good also in gaining support for his research. The situation, of course, in the centuries changed a lot, and in the case or in the framework of optical telescope, we have now, since we are a part of ISO, we have the VLTs with the mirrors of 8 meters, but there are different 8-10 meter class telescopes, both with monolithic and segmented mirrors. But of course, we have also a suite of instrumentation that usually goes from UV to the infrared to exploit as much as possible these large aperture telescopes. And we know that the future will be the ELT, the European one with a 39-meter primary mirror, almost 800 segments. And there will be at least 2 other ELTs from US, US groups, the GMT and TMT. So this will be the challenges for the near future in the ground-based telescopes. And you can see here how the primary mirror of the ELT will look like. at least in shape and size. Actually, the optical layout is quite complex with 5 mirrors, at least 2 M4 and 5, which are adaptive mirrors. So that can be changed the shape with a certain high frequency. And yes, from the considering the space telescopes, Hubble became a masterpiece in this field and was quite close to the Earth. And finally, in Christmas 2021, we had James Webb Space Telescope launched, and the exciting scientific data are just coming, and it is quite clear the future in the space telescopes, starting from the Roman space telescopes and the other projects that will allow for larger area of the mirrors and better instrumentation. So here, just to show you the difference in size of the primary mirror of Hubble and James Webb in basically 30 years. But what is the common feature is for both ground-based and space telescopes, and of course this is the same for the instrumentation, is the increase of complexity of the system. Larger size, the performances and accuracy required for facing the scientific cases, of course, make the complexity of the system larger. So I think it is apparent how the development of innovative materials and processes can be a key strategy to reduce the complexity of the systems, keeping or improving the device performances. So the approach is to simplify the device by embedding the complexity in the materials. So developing suitable materials for this with a specific, starting from specific requirements. And if we follow this path from the requirements to the developing of the materials and hopefully on sky to the telescope, it's certainly a multidisciplinary approach, which is exciting, of course, because you discuss with the people with a completely different backgrounds, astronomers, engineers, chemists, and so on. But it's also challenging because find a common language between these people is not always simple. Actually, is often difficult. So, but this is, I think, the perspective in if we really want to make and reduce the risks in the development of a new generation of telescope and instrumentation. So I just report a very simple example of this idea, and is an example that I usually propose to students. And the idea is to develop an electric blind, okay? So automatic. So I'm really lazy, so I would like to stay on my couch, and that the blind moves and decide how much light goes inside. So if I want to implement this, what I need is a light sensor to understand how much light is outside, maybe a thermometer, mechanical part, then of course an electric motor, an electronics, a power supply, and of course the development of a software that or an app for that takes all the inputs and move and act on the electric blind, and then I can stay on my couch and be lazy again after the development of the system. But if I just change the window, the glass window, and make it with photochromatic materials, the same materials we are used for the lenses, okay, actually they change the transparency according to the amount of light coming from the sun. Okay, so in this case, I don't need anymore all these elements, but I will obtain the same results. According to the illumination outside, my window will change the transparency. Okay, so basically I simplified the system that was a complex optomechanical electronic system with just a material that intrinsically responds to the light stimulus in changing the transparency, which is the property I want to tune in my system. Okay, and after this very simple example, but I really like, we move on with our materials, and actually we exploited the photochromic materials to develop optical elements, this kind of optical elements. And just to give you the official definition of photochromic or photochromism, the photochromism is a reversible transformation of a molecule of a chemical species induced in one direction or in both directions by the absorption of an electromagnetic radiation. So we move from A to B, absorbing light, and the main difference between A and B is the absorption spectrum in the visible. So the main difference is the color of my molecule, okay? And then, but what is important that the reaction is reversible. So we studied, now I go a little bit with the chemistry. We studied the diarylatens molecules. You can see here the basic chemical structure, but not really important how what atoms are. But what is important that in this form, which is called open form, the absorption spectrum is only in the UV part and no absorption in the visible. So basically the molecule, the solution with my molecule is transparent, no color, because the absorption is only in the UV. But if I shine it with the UV light, then we induce this chemical reaction, okay, this transformation. You see the chemical structure of the molecule changes, okay, and from the chemical point of view is electrocyclization. We form this central cycle. But what is important, in the closed form, new absorption appears in the visible. Okay, so now and here the absorption is around 600 nanometers. So basically in the orange red, and so I see the solution blue colored. Nicely, if I shine it my solution with visible light, then I can restore my transparent form. Okay, so I can switch back and forth between the two forms from a transparent materials to an opaque materials just by using UV light and visible light. And if I don't use any light, the molecules remain stable. So keeps the information it has. So it doesn't change the color. And we exploited such materials for making focal plane masks for astronomical spectrographs. And as you know, when you want to perform spectroscopy of some target object in your field of view of your telescope, what you need is to select the sky targets, okay, the sky object, removing the contamination of the sky and other object in the field of view, and this is performed using the focal plane mask. That usually the traditional focal plane masks are usually metal sheets with where you cut the slits, okay, in the position of your target. And of course, it's a well-established technology. You have a very high contrast, of course, between the slits and the background, the metal background. Another approach that is becoming popular is to use optical fibers, okay, that can move on the focal plane, catching the light from the sky target. It's a completely different approach that requires actually a large change in the optical instrumentation. What is nice in the case of optical fibers that you decouple the focal plane from the spectrograph, but it's certainly a more complex approach. What we would like to do is to change the traditional focal plane masks with the photochromic focal plane mask. Because in the case of traditional one, they are disposable. So when you observe some targets with a certain mask, then you have to throw away the mask and make another one. In the case of photochromic focal plane mask, you can just erase it, optically erase, and write another pattern. So it's for sure it's a more interesting approach to avoid just masks that becomes useless just after the observation. And the idea is to exploit, here is the transmittance, the transmission spectrum of the uncolored form, black one, and colored form, the light blue. Okay, so the transparent form, of course, is transparent, so the slit will be formed by the material in this transparent form, and the other part of the mask will be with the material in the colored form. Okay, so the colored form mimics the metal, and the uncolored form mimics the slits. And of course, we need to write optically such slits, and we developed actually a direct laser writing machine that just moves our focal plane mask and focus a laser in the position to write the slits in the position of my targets. This is the target we have selected on sky, and this is the final mask. These are some results we had on the Ring Nebula. Okay, we decided to have these 13 slits, okay, following the nebula, and 2 for the sky, and then we obtained the spectra, and we extracted the spectra in the H alpha region, and we also consider and measure how much was the contamination of the background okay, because the focal plane mask made of photochromic materials is not fully opaque as it is the metal mask. So we tested also the contamination of the sky out of the slit. And so it was possible to have, let me say, normal spectra using our rewritable mask. And this is really important, that we write a certain pattern, then we can erase with a UV exposure and write a completely different pattern. And this process can be performed many times, hundreds of times, without any degradation of the performances. And what is nice, that we could also make the shapes we want of the slits. So we can have, for example, curved slits, okay, again, to follow the arms of the galaxy, or any shape we have in mind that could be useful from the scientific point of view. And but the point is, of course, this is at the end, with our approach, we were able to simplify or to have to move from a mask that was disposable to a rewritable mask with complex slits, and with the possibility to miniaturize the writing system, in principle, to be embedded in the instrumentation, and to have actually an inline writing system for the slits. But the point is, how was it possible? So what was the process behind we followed to obtain such results? And if we look at the parameters we had to optimize for making such masks, we have two of them. One is the wavelength range, and the other is the contrast value. The wavelength range is what is the range in wavelength where we have the large change in transparency, from transparent to opaque. Of course, the position of the transition opaque to transparent and the width makes possible to collect spectra in specific ranges or in a wider spectral range, so that you can couple with the filters and dispersing elements. And of course, our dream is to have a material that has such transition in a very wide spectral range, basically the spectral range of the detector sensitivity or spectral response. So if we want to tune this property, we have to optimize the chemical structure of the molecule. And we can play, this is the basic structure, chemical structure of our photochromic materials, and we can play with the chemical groups. So this is just a technical chemical points. We can play with the extension of the pi electrons conjugation, or we can add electroactive substituents, so electron donor or receptor groups. But just making simpler the things. This is the absorption spectrum of the molecule in solution, and this is the absorption coefficient. And this is the basic structure. If we add, you see, such benzene rings, such groups, what we have, that the absorption that was around 525 nanometers now shifts at 570, and also we have a large increase of the absorption coefficient. And if we change one of the phenyl ring with a thiophan ring, again, we have a even more or even larger redshift and a slightly larger absorption coefficient. We can improve the absorption coefficient even more, adding another thiophan ring. And basically, we are now with a large absorption in the red part of the spectrum. We can also play with the substituents. So we start with this molecule, basic molecule with the phenyl ring. You see, now we added this amine group, and nicely we have a really huge shift in the red and increase in the absorption coefficient. And by making an asymmetric molecule with a nitro group on one side, amino group on this side, again, we can be more in the red, and also we can have absorption in the blue, secondary absorption in the blue. So this, of course, this to say that if we work with good chemists, you can ask for the optimization of the chemical structure, and this to cover basically all the absorption, the visible absorption spectrum with specific photochromic molecules. And these are all the absorption spectra of the molecules synthesized, starting from our needs. So the goal was to develop the focal plane mask with an absorption spectrum or a transition from opaque to transparent as large as possible. And we call it a Lego chemistry because for us it's just to combine pieces of Lego but if you say this to the chemists, they are not really happy because they spend hours and days in the laboratory to synthesize and purify the molecules, and usually they produce milligrams of molecules, but you ask for almost grams of molecules. So it's not always simple to ask a large amount of molecules from to the chemist. The other point is the contrast value. So it's true, we want a change in transparency, but we really want that in the opaque part, the mask is really opaque, no contamination from the background. The contrast is just defined as the transmittance of the transparent form divided by the transmittance of the opaque form. You see here. And of course, the higher the contrast, the lower the sky contamination, as we said. And we need the large contrast in a wide spectral range. And if we look at, of course, there's a very simple formula. We immediately understand that the contrast is driven by the transmittance of the opaque form. Okay, TB, so the colored form, the transmittance here is the driving parameters. And actually depends on the absorption coefficient, depends on the concentration of our molecule in the film and the thickness of the film. And so we have to, the absorption coefficient depends on our molecule, and then we can play with the concentration and thickness. So the point is, okay, we can make thick film with a large content of photochromic molecule, and easy, we have our film, our photochromic mask with a very high absorption, so very low value of the transmittance in the colored form, so very nice contrast, and we can perform the observation we want. in principle, this is true, but at the moment we have just the molecule. We don't have the material. We have just a set of molecules synthesized by good chemists, but we don't have the final device, the film with optical qualities and so on. And so this is the optimization of the molecule was just the first step of our process. And then we have to move from the photochromic molecule to the film, okay? And in this case, we follow, or we can follow, two strategies. One strategy, which is the simplest one, is just to make a blend. So we take our molecules, the photochromic molecules, we choose a matrix, a polymer matrix, we just mix together and deposit the plastic film, okay, which is now doped with our molecule, and then we have our film. But we can develop a different approach, which is the development of polymer, so let me say, plastic materials that are already photochromic. So it means that the polymer itself contains a chemical unit that is photochromic. And here we don't need any polymer support matrix. So it's really interesting, this approach. And they have both some advantages and disadvantages. We start with the blend approach. It's very simple, as we said. We have our polymer matrix, then can be plexiglass, polystyrene, a classical polymer for optical application. We put in a solvent together with our molecule, we mix, and then we deposit. The main issue here is that the photochromic molecule and our polymer matrix must be compatible. So the solubility of our photochromic molecule in our polymer matrix must be as large as possible. And this is not always true. So I can optimize the chemical structure of my photochromic molecules, but then if it's not compatible with my polymer matrix, I just have to reduce the concentration of my molecule, and then the change in transparency, so the final contrast will be low. Also, if the molecule is very nice in terms of absorption coefficient, so the good combination, polymer matrix and molecules, to have a larger contrast is not always simple. Actually, we were able to have a nice films with a high contrast using cellulose acetate butyrate, a cellulose-based polymer, and combining more than one molecule, photochromic molecule. And you can see here the 20% of concentration of our photochromic molecule, or for 3.5 microns, but you see how the colored form is really dark. So we could really achieve a very large contrast in this case. And the other approach we followed was to develop photochromic polymers. So you have to think about a polymer, so a very long molecule with a repeating unit, where you have in the chain, in the polymer chain, you have your photochromic unit, and you can switch in between the polymer in the uncolored or one color to the other. Okay. And in this case, of course, the concentration of the photochromic unit in the polymer chain, in the material, is very large, because you just have the photochromic unit, and so you can really it's really easy to have a high content of photochromic molecule in the film. And we developed photochromic polyurethanes. Maybe you know polyurethanes for foams, for inks, or polyurethanes is really a versatile polymer employed in many common devices we use every day. But we can make also optical quality polyurethanes. This is just the chemistry we used. I don't go, of course, in details, but just that we have one of the components that reacts in the polymerization reaction is our diarrhea, is our photochromic unit. So we have two components, we mix together, we deposit it, and we have a thermal post-processing, and we have our nice films. And what is interesting, we can mix more than one photochromic components and have a system that, for example, can be switched in different colors, or have the full switched system. So again, we can increase the versatility of our films just by optimizing the composition of our photochromic units in the polymers, and have a large change in the optical properties, and in this case without the risk of segregation, so the risk of incompatibility between the photochromic unit and the polymer, the plastic material that gives the mechanical properties and forms the film. And actually, we combine everything, all the experimental results we have. So the absorption spectra of the set of molecules we had from the chemists, the composition of the film thickness, the amount of the fraction of the molecules we had, and the illumination condition to convert the material from the uncolored to the colored form. So we developed this software tool that provides us the contrast function, okay, or the contrast value of our final film, starting from some real experimental data coming from the molecule we have. So we have the molecules, we have the polymer system, and we can really calculate the final contrast that the film will have, and then if it's suitable or not for our final application. So this approach is really useful because it allows for the for saving time and materials, because you can predict basically the performances of your final mask and so on, just by starting from these software tools. And of course, we didn't do only focal plane masks with the photochromic materials, but we developed other devices just we develop some tools for the optical testing of optics, so a point diffraction interferometer, okay, which is a very simple interferometer for measuring the wavefront of an optics, okay, and we developed extensively computer-generated holograms for optical testing. So again, where you can write an hologram that produces a wavefront equal to the wavefront of a complex optics, a spheric optics, or freeform optics. So instead of having the real optics, you can build the same wavefront using an hologram, and then we develop some masks for optical lithography. But again, exploiting always this change in reversible change in transparency of our materials. Okay, just so I think so. I would like to conclude. I have another topic, but then it will be too long. So I would like to conclude in this way. The common process for the holograms or for the mask and so on is the design. We have the you print or you make the device. You have a post-processing, and then you have the device. We don't want. We would like really to have a system that just requires the simply optical writing of our patterns and have the final device. But what we would like to have also is the possibility to use the system many times, so we can erase our pattern and print a new one, and so have this circle. So basically, we developed a simple and reconfigurable platform for masks, waveguides, holograms, and so on, based on our photochromic materials. And I just go to the, let me see if I can, okay, I go to the conclusion that we can say that, of course, it's clear that we have an increase of the complexity of our tools, our telescopes and instrumentation. It's important to develop new materials and processes in a multidisciplinary approach, with a multidisciplinary approach. And I hope to have shown you how the photochromic materials is a good example in this sense. And what is really important is that the optimization of the device and at the end, the real use, or the fact that you convince the engineers to use the new devices or the new technology in the final instrumentation starts from the good understanding of the material properties and a good understanding of the requirements. The question is, when should we start this kind of activity? Because I mean, it's high. The risk of failure is really large of using this approach. So when we should start, and how to support this kind of activity that of course, you have some publications at the end. This is nice, more sometimes, and but then it is worth to develop some programs for these enabling technologies, and give a certain time scale or roadmap to have, I mean, in accordance to the time scale of the new instruments and telescopes. So this is, I think, really important to understand also at the national level too. And yes, I think I finished. I should be in time. Okay.
Yes, you are perfectly on time. So thanks, Andrea. And please, if you have questions, unmute your microphone and ask your question yourself. Ivan, please go on.
Okay, ciao Andrea, thanks for your interesting talk. So I have two curiosities, let's say. The first one is if you are thinking to use these new, let's say, materials for applications different from spectroscopy. For example, when you mentioned the CGAs, the holograms, so I was thinking to laser applications and so on. So the first curiosity is that these materials can have applications different of, let's say, the spectroscopy. And the second one is more related to the materials themselves, and is related to their thermal behavior. So the temperature play a role in the futures of these materials. I would say that if the bandwidth can change with the temperature and the contrast. So these two. Thanks.
Okay, for the first question, yes, we used the no, this is sorry, I go back to the box. Okay. We use such materials for example, for making waveguides. Okay, and the idea is, because the point is, I showed just the changing transparency of the materials, but if you go in the near infrared, they show a change in the refractive index, in the real part of the refractive index. So basically, what you can think is to write a waveguide pattern you want working in the near infrared. So let me say from 900 nanometers to 2 microns, basically, and with any shape you want or any path you want. So waveguide couplers and so on to perform again different tests. So we used it as holograms. Again, we use the computer generated holograms for optical testing. We made similar holograms working not in amplitude, again exploiting the changing transparency, but phase holograms in the near infrared. So the application can be different. It can be also possible to have a sort of tunable filters, where you can tune the transparency in the target spectral band. For example, can be useful to balance some signals of different targets in the sky. If you want to, instead of, for example, defocusing the system to spread the signal or more pixel, you can just decide where to make more or less transparent and have a balance of the signal on the detector. So the possibilities can be many, and what is not possible, I mean, in any case, the systems are not fast, in the sense that the transition takes some seconds or minutes, so it's not really, cannot be used as a fast systems or adaptive system and so on. For the temperature side, these systems are, the diarelators are called P-type photochromic materials, so it means that both states are stable, thermal stable. Usually you don't see any effect for this kind of devices I showed up to 60, 70 degrees. Then if you increase toward 100 degrees and so on, that you have two competition. Can be a decoloration, but it's not so probable. The stability is really, but you could have or start to have a degradation of the materials. It's an organic material, so the stability with the temperature is always an issue that we never optimized the system for working at let me say relative higher temperatures.
Okay, thanks.
Yeah.
Other questions? Andrea, I have a few curiosities. Oh, there's Gianluca probably.
Yeah, ciao Andrea.
Oh, ciao Gianluca.
For question, thank you very much. Very interesting when you were presenting. It came in my mind a lot of application could be possible. A question similar to the one of Ivan, maybe you already answered in some way, is what is the power you experimented so far that this material can tolerate in some way, at least at visible light. And other points are about the lifetime of this material, the durability of this material. Do you have any information about that?
Yeah, okay. For the first, let me say, when you use such a device in the visible, so exploiting the change of color, of course, the light which is absorbed also induce the transformation. So it means that the visible light that is blocked by, let me say, the focal plane actually it will erase the mask. So in this case, of course you cannot use very high light flux, but I mean, consider that when you write the slits in terms of seconds and so on, you focalize, let me say, a few milliwatts of lasers on 30 micron. So the radiance required to switch the materials is quite large. So the stability is in the visible with normal application, both in interferometer, or on sky with the mask. For the mask is not an issue. In the visible, if you move to the near infrared, where you just have a phase contrast, the change in the refractive index, no absorption, of course, you don't have any effect of the radiation. So they are stable for without any. You can use also quite high power signal. So you can couple, for example, a neodymium YAG laser at 1 micron. You can couple tens of milliwatts in a waveguide without any degradation of the waveguide. In the visible, of course, yes, you have this fact that the light absorbs also induce the transition. But we didn't see any effect in the application we had. For the endurance of the materials, we measured, we developed a few years ago or measured the fatigue resistance, so the number of cycles we could perform before the degradation, and we easily reach hundreds to hundreds cycles of the. So it really depends on the wavelength, UV wavelength you use for erasing the mask. We develop a sort of chemical physical models to explain the behavior of the different molecules. And so yeah, let me say you can use such devices 100, 200 times without any issue.
Okay, thank you, Andrea.
Yeah.
Another question, but maybe we can discuss.
Is there anybody who has some question? Otherwise, I'll just ask one myself. Andrea, I think that you made it clear the point that this is most a work of development. But how diffuse? I mean, are there perspectives for other, or groups that that are working on this kind of development that we will see soon or sooner or later some kind of these technologies applied to some telescope?
Okay, for the photochromic materials, I think we are the only group that try to use them for real devices. But for example, it has been studied deeply the liquid crystals devices for making polarizers, for making apodizing masks and so on. I think groups in Netherlands made this kind of study. And again, was a similar approach. So starting from the optimization of the liquid crystals devices and then to develop the final device. I don't have I'm not really aware of the final results they have. Similar things or approach different, for example, have been used for the anti-reflection coatings, not based on multi-layers, but with nanostructured layers, so a sort of meta surfaces, and that allows for a broadband anti-reflection coatings, just with a simple layers, which is not which has a specific optical properties due to the nanostructured surface. I think in general that we should look more in details into metamaterials, so meta lenses, meta surfaces, which are really, so you can make negative refractive index materials, this kind of stuff. So there are a lot of interest. There is a lot of interest in such materials worldwide, but I'm not sure. For sure, in Italy, we are not really involved in this. Also at the European level, in the US, I think there is more interest also from the astronomical community on this. So I'm sure. I think we should look more in or to establish more collaborations with this kind of other. But again, is then I will refer to my last point in the conclusion. So when and how to support, in the sense that at the end, there isn't, for sure, there isn't an enough level or a sort of roadmap or something. I say, okay, develop new technologies, just new ideas. With of course, you must have a time scale and say, I cannot provide money or support collaboration. Can be a support collaboration also a PhD grant. I mean, not just money.
Yes, okay.
And say, okay, I can give you some years to try to develop something, of course, reasonable, but most of them are by chance. I mean, maybe you meet a friend or say, what are you doing now? I'm developing such materials. Maybe they can be useful in this. Also for in my field, this kind is the approach instead of a more structured one. This is, I think, but metamaterials, I think, could be keywords for the future.
Yeah, it's gonna be interesting. Yes.
Yeah.
Okay. Let's thank Andrea again. Thanks, Andrea, for the very nice and interesting talk. Actually, let me stop recording, and so